In this lecture, I'm going to give you one example on how to use the PFC algorithm. Or how to use the PFC algorithm. So the system considered, so it's a discrete time system. So it is xt plus 1. So the A matrix here is 0.8, 0.1, 0.1, 0.9 xt plus, so 0.10 yt. So the A matrix is defined here. And the B matrix is defined here. This is the C matrix. So the YT, so here T plus 1. So YT, so the C is 0.1, 0.9 xt. In this example, let's assume, so the xt, the state x time t is 0, so therefore, so yt at time t is 0. So it's a vector. So yt is just a scalar. Then here, so let's assume, so the set point, the current state is 0. The set point is RT. So RT is 1. So therefore, we need to find a control to change the output from 0 to 1 to track the set point. So here, so the R is defined as 1. So this is the problem formulation. So the first step, if you go back to the slides. So based on the algorithm, so first we need to find the row matrix, and the row vector, and then the Y matrix. So the row vector is the reference trajectory minus we can call this natural response by assuming the control input is 0. The reference trajectory is generated this way. So we use the first order system. So the reference trajectory is generated in this way. So Wt plus K is Rt plus K minus, so the alpha K Rt minus Yt. So here we choose the alpha is 0.5. So here is alpha. We use the A to represent alpha. So A is 0.5. So we know at current time T, so Y is 0. Then we need to update as next time, so T plus 1, we need to update. So the Y 0 here is will not be 0. So this is formula. So then we calculate. So let's assume, so here, so the prediction horizon is N is 4. So therefore we need to calculate Wt plus 1, Wt plus 2, Wt plus 3, Wt plus 4. Okay. So here we use to calculate the W. So W, T plus 1, T plus 2, T plus 3, and T plus 4. And the prediction horizon N is 4. Then we can also calculate, the free response, even though here, so assume the initial state at time t is 0, but then at the next time t plus 1, then the xt plus 1 will not be 0. Then we still need to calculate then the natural response. Then here, so this will be CA xt, so CA xCA square, So sorry, so here will be C xt. So this is the, no, so this is a xt. So this is a t plus 1. So this is a t plus 2. Then this is the t plus 3. So we see a power of 3 xt. Then this t plus 4 will be ca 4 xt. And so this is so then we use the w, so minus this y, I call it yf. So w minus yf. If you screw down, okay, so here's wy minus yf. It will be, so the row vector here will be the row vector here. The row vector. So let's assume so that the noise, the disturbance is 0. So make it simple. Then we have the row t plus 1, row t plus 2, and row t plus 4. So this is the row vector. Then let's assume here, so we use a polynomial type basis function. We use a polynomial type basis function. Then let's assume, so NB here, it is 3. Okay? We use 3 basis functions: steps, ramps, and prep. So therefore, okay, so the UTT, so the UTT, so first maybe let me write in this way. So this is a bit 1k is 1. So bit 2k is k. So bit 3k is k squared. So therefore we have this matrix. So this is when k is 1. So we have, so k 0. So for UTT, so UTT, so will be, so mu 1, so bit 1, 0 plus mu 2, bit 2, 0, then mu 3, bit 3, 0. So then bit 1, 0 is 1, bit 2, 0 is 0, bit 3, 0 is 0. This is time when k is 1, 0. And when k is 1, so this will be ut plus 1. Then we still have mu 1, so bit 1, 1 plus mu 2, bit 2, 1, and plus mu 3, bit 3, 1. So then in this case, so k is 1, therefore we have 1, 1, 1. Then when k is 2, then we have mu 1, so bit 2, bit 1, 2, bit 2, 2, bit 3, 2. Then we have the 1, when k is 2, 2, 4. Then the last one, so when this is k is 2, so when k is 3, it will be ut plus 3. You have mu 1, so bit 1, 3. So 1, then bit 2, 3, 3, then bit 3, 3. So here is 9. Then for the forced response, okay, so we only need to calculate. So we only need to calculate the response of the system for the basis function, Then it will be scaled by mu 1. It will be scaled by mu1, mu2, and mu3. So therefore, this YB matrix. So here, so this YB matrix. So let me specify this Y bat matrix. This Y bat matrix will be something like this. So Y bat. So the first, so we assume the other initial condition is 0. Okay. So this is the false response. We assume the initial condition is 0. So we have Y beta 1 t plus 1, then will be, so this at a time t plus 1, so y beta 2 t plus 1, then y beta 3 t plus 1. So this corresponds to time yt plus 1. Then for the next row, we have y beta 1 t plus 2, y beta 2 t plus 2, y beta 3 t plus 2. So it's corresponding to time t plus 2. Then for the next row, we have y beta 1 t plus 3. So y beta 2 t plus 3. Then y beta 3 t plus 3. So this is to calculate the forced response at time t plus 3. Then the last one will be y beta 1 t plus 4, y beta 2 t plus 4, then y beta 3 t plus 4. Okay, so each of this column can be calculated independently. So the first column is corresponding to the control input here. So the second column is corresponding to the control input here. So this is corresponding to the first control input. This is corresponding to the second control input. Then the third column of YB corresponding to this control input. Okay. Then, as you know, so this one is kind of like a fixed. Okay. Once we calculate the Y beta matrix, it's fixed. It's independent of T actually, because we assume so the 0 initial condition. So 0 initial condition. 0 initial condition. So xt is 0, xt plus y is 0, so xt plus 2 is 0. Then the control inputs are fixed as well. So therefore, this matrix, once we calculate this matrix, okay, this is matrix fixed. So in other words, this matrix only needs to calculate once, okay? As we can see from the MATLAB code. Once we calculate the mu, then for the next iteration, so we just use the mu. We don't need to recalculate this mu again. Sorry, not the y. Okay, we just need to calculate y once. Okay, y once. Then we don't need to calculate y again. We only need to update the w. So there's a reference trajectory and this free response because the next time t plus 1, so the xt is not 0, so yt is now 0. So therefore, we just need to keep updating yt and xt using the system equation. Then now let me show you, so a very simple MATLAB code, okay, how to calculate this Y beta matrix. So let's start from here. So we have the defined is A and B and C. So at the beginning, we assume so the xt is 0, 0. So the reference set point is 1. For the output, the initial state is 0. So initial output is 0. So this alpha is 0.5 to calculate the reference trajectory. So here we define the xtem. So that basically saying, so for each sequence, okay, for each control sequence, we need to independently calculate the output. Independently calculate output. So for example, for the first column, then the next output will depend on the previous output, but it's independent with the control input in the second column. So this is something you have to pay attention. Okay. So we need to calculate each column independently. But within each column, so the second output will depend on the first output, because the second state will depend on the first state, and the third state will depend on the second state. But between columns, it is independent. So they are independent. Okay. So that's why we define this xtem for each column. So I from 1, 2, 3. Then so we do this for the for is a time horizon. So therefore we calculate yt plus 1, yt plus 2 until yt plus 4. So this step, so to calculate the reference trajectory, calculate reference trajectory, so using RT plus K minus alpha K times RT minus YT. So this one, so this is the natural response. So natural response by assuming all the control inputs are zero. All the control inputs are zero. So it'll be CA power of K. So X0 again. So this is the state at time T. So at the current it's zero, but then at the next time step T plus 1, it's not zero anymore. Then this step to independently calculate each column, independently calculate each column. Then first, let's give in the control input. So basically corresponding to here. So 1, then I is 1. So maybe we can run this step by step. You see, so the first value of U is 1. So this corresponding to K. So here, so the K is 1 basically means that K is 0. So K is 1 corresponding to K is 0. The first one is 1. Then we use this control input to calculate to this state. Then this is the Y. Then this is the Y. So first the Y. So that is Y beta T plus 1. Y beta T plus 1. Then we do this one again. Then the second one, so here 0, is calculate Y beta T plus 1. Then the U here, so U here is 0. U here is 0. Let's do one more. So U here for the third column, so U is 0 again. And the Y is 0 because we assume 0. So for calculate the forced response, we assume 0 in the conditions, and with 0 inputs, output is 0. The next, when K is, so here K is 2, basically means corresponding to, so K is 2 here. Then here, basically, the K is 0, so UT plus 1. See, so the U is still 1. And the new X here, so that's Y beta 1 T plus 2 with the control input 1 and 1. You can see in this case, So the control input is not 0 when k is 1. So control input is 1. Then this is the y here. Then this u is 1. So this one corresponding to y beta 3 t plus 2. So let's continue. So here u is 1. This y. This one corresponding to y beta 1 t plus 3. So now this u is 2. This when I is 2, this is the second column. Now we calculate this y beta 2 t plus 3. So beta is 4, so that's the third column. Then this is the y beta 3 t plus 3. So u is 1, first column. So this is beta y1 t plus 4. So this is the output when the input is 1, 1, 1, 1. Here u is 3. Then this is y beta 2 t plus 4. So that's the output with the control input is 0, 1, 2, 3. So this one is u is 9. And we have the last one. So y beta 3 t plus 4. When the control input sequence 1, 0, 4, 9, assuming 0 unification. Okay, now we are done. Then we can calculate the control input. We have the y matrix, then calculate the control input. So that's mu is corresponding to, so mu1, mu2, mu3. So here the mu is mu1, mu2, mu3. So we can also see here, so let's see the y. You see, so this is a y. So it is 4 by 3 matrix here. So 4 by 3 matrix. So the mu, you can see from the mu here. So this is a mu1, this is a mu2, so this is a mu3. Then based on the control here, so we only apply, so here, so because the beta I0, so we have, so the beta 2, 0 is 0, so beta 3, 0 is 0, so therefore we only use, so mu1 here, we only use mu1. So we only apply the mu1. Okay, then we repeat for the next time when the t plus 1, so the control input is only the mu1. So the mu1, so then the beta 1, 0 is just 1. So therefore the UPT is just mu1. Then we simulate the system using the A, B, and matrix and the Y. Then we repeat this whole process. Then recalculate the reference trajectory at time t plus 1. We need to update this y. We need to update y. It's not 0 anymore. Then we need to calculate the free response. Again, this is x0. It's not 0 anymore. We need to use xt. Then we don't need to calculate this y again. We need to update this w reference trajectory, the free response, then calculate new mu. Then we just apply the first one and repeat this whole process. Then we can plot the output. Okay, you can see from here. So let's repeat this whole process for 20 time steps. So initially the y, we plot this y. Initially this y0. So roughly about like 10 time steps, it reaches the set point.